So the speed limits. Okay. Okay, so what's the maximum speed at which the car goes into a skid? Okay, so will it change from vehicle to vehicle? All right, once again, common sense will say yes. Using physics, you can argue either way. All right, so by using physics, if you can argue either way, more than likely it's not going to matter. If you can make a valid argument using physics, you can make a valid argument. One argument is the lighter vehicle is going to be able to negotiate at a faster speed because it's got less inertia. The second argument is the heavier vehicle is going to be able to negotiate at a faster speed because it's got more friction. Friction depends on the mass, it depends on the weight. All right, so if you argue either way, which means that it's really not going to matter. Let's check to see if the mathematics is going to back that up. All right, so this is going to be problem number. Okay, so this is going to be problem number 3. Problem number 4 is a mathematical. Problem number 3 is a more derivation-based model of it. Problem number 4 is a numeric way of doing it. Okay, so I'm more interested in problem number 3, so let's focus on that one. Problem number 3, the worksheet. All right, so these are standard physics problems. Okay, so does the maximum speed up for a vehicle change from vehicle to vehicle in regards to how fast you can negotiate a curve without going into a skid? All right, so once again, depending upon how you're looking at it, you can argue either way. And the conclusion is it shouldn't matter. So the question is, why not? All right, so I'm going to draw this out on the side because we need to come up with a force diagram for this. So it's going to be circular motion. All right, so it's going to be circular motion. So this is moving at this speed, so there's going to be a centripetal force acting on it. This is going to be the static frictional force. Okay, as soon as you maximize the static frictional force, this thing is going to go into a skid. All right, so what is the maximum speed at which you can negotiate a curve? And there are no numbers involved, so we're just going to come up with a mathematical expression for this one. All right, the way to do it is the static frictional force, in this case, is going to be the centripetal force. All right, so we got a mathematical expression for the centripetal force. And we also have a mathematical expression for the static frictional force. All right, so these two will be equal to each other. All right, so they are the same. mv squared divided by r. Okay, r is the radius. It's going to be mu sub s times n. All right, so solve for v. All right, so get rid of m. And then get rid of r. Okay, so we got v squared mu sub s times n times r divided by m. Get rid of the square. And just stop at this point. Okay, so when you stop at this point, in this case, you don't have any numbers. This is the way we normally would do physics problems. We don't usually worry about the numbers that much until we're done with the problem. And then at that point, if you want to test to see if the solution is correct, that's when we worry about the numbers. Okay. Just conceptually, I'm looking at it. If I stop at this point, I want to say heavier the vehicle is, the slower the speed is going to be, which means that the heavier vehicles will go into skid at a lower speed. Okay, so that kind of conceptually, if I were in that camp, I would make that argument. If this is a bus or something, I'm not talking about rolling over. I'm talking about going into a skid. The heavier vehicles will go into a skid at a lower speed. That's the argument that I would make. Lighter vehicle will go into a skid at a higher speed. Okay, so I would say initially most of you guys would agree with this, and that would be the end of it. But you cannot make that argument as yet because N is a reaction force, guys. It's a reaction force to what mass does in this case. Whether it's a reaction force because of the weight or it's a reaction force because how badly the mass wants to go in a straight line at a constant speed. So N is going to be sensitive to the mass, which means that once again, we expect to see a cancellation. So where do we get the M from? All right, so we end up getting our N in this case from what goes on. All right, so N is what we're going to be focusing on. N is going to be a reaction force to the weight in this case, right? Okay, let me just use red for the forces. All right, so this is your W. My W looks shitty. which is going to be mg, and n is a flat surface, is going to be in the upward direction. And then we're looking for n. So look at the net force on the y direction. N is up, w is down. Mass times acceleration on the y direction, and there's no acceleration on the y direction. All right, so which means that n is the same as w, and w is the same as mg. And then boom, just substitute back into that formula. And when you do that, what do you get? You end up getting an expression that looks like this. N is the same as mg. And then we have our r in the denominator. Once again, we have the mass. And then immediately you notice that these masses are the same. So which means that the masses will cancel. All right, so the final expression is going to look like this. That's it. So how fast the vehicle negotiates a curve does not depend on the mass. It's not going to depend on the mass because of a simple reason that the mass doesn't matter. Okay, so larger the mass is, the larger the friction is going to be. Okay, so the only thing that really matters is the radius of the curvature. All right, so the same quality tires, larger the radius is, the faster you can negotiate it. Smaller the radius is, slower you will negotiate it. For a given radius, better quality tires will allow you to be able to negotiate it at a higher speed. All right, so it's all common sense. All right, so the conclusion is, I'm going to put the emphasis here. The wider the turn is, the faster you can negotiate it. And obviously, sharper the turn is, slower the speed at which you can negotiate a curve without going into a skid. And so those are the conclusions. Okay, so this one's too sharp of a turn, which means that it's got a radius which is fairly small. Which means that the maximum speed with which you can negotiate it is relatively small. Okay, so the next question is, how did they come up with those kind of weird speed limits? Let's focus on that one briefly. Okay, so number one, when they designed the road, obviously they know the coefficient of friction for static friction. It's built accordingly, and they determine the radius, and then they build the road. If it's an on-ramp, off-ramp, here in Chicago, obviously you got some speeds. They're usually about 45 miles per hour, right? All right, so the off-ramps, on-ramps are about 45 miles per hour in general. All right, so what do? They do the calculations, and then they come up with a number, usually, which is about 60 to 65 miles per hour. It's about 65 miles per hour. On the side of the road, they will put down 45 miles per hour. Okay, so what happens? So I hit the ramp, and when I hit the ramp, if it's 45 miles per hour, I would never go at 45. It's just annoying. Okay. By the time I reach the ramp, it's probably I'm slow down to about 70 miles per hour. And then I don't want to hit the ramp at 75. I will just slow down to, if it's 45, let's say I'm going about 50. And then you can actually speed up at that point. You can go up to 55. All right, so you got static friction. And then when you go up to 55, static frictional force is going to go up further. You can even go up to 60. And then what happens, the static frictional force is going to go up further. And then you can, at this point, it's going to be 60. And then when you get up to 65, it's going to get larger. At some point, you will maximize the static frictional force. Okay, how do you know that you're maximizing static frictional force? Tires will start to squeeze, guys. At that point, you have to go easy, which means that you're maximizing the static frictional force in 1 or 2 or 3 of the tires that you have, which means that you're about to lose control of the car. At that point, you have to slow down, because all 4 tires start to squeeze, which means that everything is going to go kinetic at that point, which means that you will go in a straight down at a constant speed. So they do the computations. They know that the maximum speed at which you can negotiate is 65 miles per hour. And they will put down 45 miles per hour on the side of the road. The reason why they do that, because the road conditions will change depending upon the weather conditions. Obviously, if it's raining, the coefficient of static friction is going to go down. So this number is going to go from 65 to roughly about 55 miles per hour. If it's snowing or whatever, it's going to go down further. All right, just to be safe, they will put down 45 miles per hour. Okay. And then even at that point, they don't really trust you, the engineers, the civil engineers, do not even trust you with that. So they do something extra. What they do is they also bank the road on purpose. All right, by banking the road, they make sure now you can probably negotiate at 70 to 75 miles per hour. Okay, so they will give you plenty of room just in case. All right?
Modified
in case you're
ZR1 Corvette.
In case you're speeding. All right, I don't want you to go off the road.
Capable of spectacular speeds.
All right, so this thing is banked for like 200 miles per hour. Our ramps here in Chicago, they're banked for about 70 to 75 miles. All right, if you see it banking like that, that means that you can really throttle up.
Above 200.
All right, so that's actually cute. All right, take a break for 10, be back within 10. Okay, so resume recording. All right, so when they kind of bank this would be an interesting problem for you guys, for the engineering students. So all that for engineering physics. So the maximum speed with which you go into a skid does not depend on the mass of the vehicle. As soon as you maximize static frictional force, that's when you're going to skid. So the minimum speed with which the vehicle goes into a skid does not change from vehicle to vehicle. I meant to say the minimum.
Worries out of your mind.
For whatever reason, guys, while you're negotiating a curve like that, the car goes into a skid, a couple of things that you can do.
Focus on steering the car where you want it to go. But that's only part of the battle. What you do with your feet counts too. If you go into a skid, he says don't slam on the brake or the gas.
Turn your hands, now back the other way. There you go. Now, see how you just went back to the gas?
I did.
Yeah, everybody does that. Everyone wants to be Mario Andretti. And the first thing is to go back to the gas. So what we're teaching here is don't touch any pedals.
It took a lot of practice, but after several attempts, I got the hang of it.
Get ready for it. Here it comes. Look at those hands. Yes, pause, recover. That's absolutely perfect. There it is.
All right, so what's the idea behind it? So let go of the brakes. Because the car is skidding, which means that you're utilizing static friction. When you let go of the brakes, what happens? The tires start to roll. So which is going to be static friction.
Worries out of your mind. Focus on steering the car where you want it to go. But that's only part of the battle.
And so that's what you need to do. All right, we've done the computations for that one.